Logistic regression is one of the most important models in machine learning, and it's all about probabilities. Instead of predicting just a class, it estimates how likely an input belongs to one. We'll start with binary classification, where labels are modeled using a Bernoulli distribution. Then we'll see how the sigmoid function connects linear models to probabilities through odds and log odds. Next, we'll look at cross-entropy loss and how gradients drive learning. We'll compare optimization methods, from gradient descent to second-order approaches like Newton's method. Finally, we'll cover key extensions, including L2 regularization and multi-class classification with softmax. Let's start with the basic problem setup. Each point here is a data example, and the color shows its class. Our task is to predict a binary label, 0 or 1. You can see that the two classes tend to cluster in different regions. When a straight line can separate them, logistic regression is a natural model to use. Logistic regression turns a linear score into a probability using the sigmoid function. You can think of this score as a weighted sum of the input features plus a bias. The sigmoid squashes any real-valued input into a number between 0 and 1. Large positive scores push the probability toward 1. Large negative scores push it toward 0. So the model's output can be interpreted directly as the probability that the label is 1. So far, we've seen how logistic regression outputs a probability. The model starts by producing a probability using the sigmoid function. We can rewrite that probability in terms of odds, how likely the event is to occur versus not. Taking the log of the odds gives the logit, which turns out to be a linear function of the input features. So logistic regression is linear in log odds space and probabilistic in output space. Now let's put everything together. Logistic regression maps a linear score to a probability using the sigmoid. That linear score defines a straight line in feature space. Where that score is 0 on the line, the model is exactly uncertain, a 50-50 probability. Each side of the line corresponds to a different predicted class. To train the model, we need a loss that measures how well it fits the data. For binary labels, each outcome is modeled using a Bernoulli distribution. Training means maximizing the log likelihood of the observed labels. In practice, we minimize the negative log likelihood, also called cross-entropy loss. This loss heavily penalizes confident but incorrect predictions. To train logistic regression, we need the gradient of the loss. We start from the cross-entropy loss for binary classification. The predictions come from applying the sigmoid to a linear function of the inputs. Taking derivatives looks messy at first, but the structure is very regular. After applying the chain rule, most of the terms cancel out. What remains is simple. Each data point contributes its prediction error, scaled by its features. In matrix form, the entire gradient collapses to one clean expression. If we average over samples, we just scale this by 1 over n. The bias term follows the same logic. Its gradient is simply the sum of prediction errors. Again, everything depends on predicted probabilities minus true labels. In practice, we don't treat the bias separately. We simply add a row of 1s to the data matrix. Then the bias becomes just another weight, and the entire model can be written as a single matrix multiplication. With these gradients, we can now update the parameters using gradient descent, where eta is the learning rate. Now let's look at the second-order derivative of the loss. Recall that the gradient depends on prediction error and the input features. The Hessian is simply the derivative of this gradient. When we differentiate again, only the predicted probabilities depend on the parameters. The key term is how the sigmoid's output changes with the weights. This turns the Hessian into a weighted sum of outer products of the inputs. In matrix form, this becomes a very compact expression. Because this matrix is always positive semi-definite, the loss is convex. That means logistic regression has a single global minimum, no local traps. This structure allows us to use Newton's method, which uses curvature to choose better update directions. In practice, we don't invert the Hessian. Instead, we solve this linear system to find the update step. This is known as the Newton IRLS method. And just like before, the bias is included as part of the weight vector by adding a row of ones to the data matrix. Now let's see how logistic regression is actually trained. We start with small weights and a poor boundary. Each step nudges the line to reduce the loss. You can see it gradually move to separate the classes. The loss on the right steadily decreases. These small steps follow the slope until the model converges. This is the most common way logistic regression is trained in practice. Now let's train the same model using Newton's method. Newton's method uses curvature, not just the gradient. The boundary moves quickly toward the optimum. The loss drops in only a few steps. It converges in far fewer iterations than gradient descent. But each step is more computationally expensive. In practice, this makes it ideal for smaller or well-conditioned problems. Now let's look at what L2 regularization does to logistic regression. As regularization increases, the weights shrink toward zero. The decision boundary barely moves because the weights and bias shrink together. What changes is the model's confidence. Smaller logits stretch the sigmoid, pulling predictions closer to 50-50. So L2 regularization changes the model's confidence more than what it predicts. Now let's switch to L1 regularization. With stronger L1 regularization, some weights are driven exactly to zero. The decision boundary changes noticeably. Eventually, one feature and the bias vanish, leaving a vertical line at x equals 0. The model is now ignoring that feature entirely. This is feature selection. Logistic regression naturally extends from two classes to many classes. Instead of a sigmoid, we use the softmax to produce probabilities over all classes. Training uses multi-class cross-entropy over these probabilities. The weight vector now becomes a weight matrix, one column per class. The gradient keeps the same structure, data times prediction error. Even the Hessian has a similar block structure based on these probabilities. And the binary case is simply the special case where the number of classes is 2. Let's evaluate logistic regression on a real data set. On the left is the ROC curve, receiver operating characteristic. The x-axis shows the false positive rate, and the y-axis shows the true positive rate. Each point on this curve corresponds to a different classification threshold applied to the predicted probabilities. As we lower the threshold, we catch more true positives, but also introduce more false positives. The AUC, area under the curve, summarizes how well the model separates the two classes across all possible thresholds. If we now fix the threshold at 0.5, which is different from the false positive rate being 0.5. We get this confusion matrix showing the actual classification outcomes. To understand how the model separates data, we project the test set into 2 dimensions using PCA, Principal Component Analysis, which will be covered in a future video. To summarize, logistic regression models binary classification as a probabilistic Bernoulli process. A linear score is passed through a sigmoid function to produce a probability. These probabilities have a simple structure. The log odds are linear in the inputs. We train the model using cross-entropy loss, whose gradient vectorizes neatly as data times prediction error. We optimize with either gradient descent or Newton IRLS, which converges in fewer iterations by using curvature. Regularization controls the model's confidence with L2 and can even remove features entirely with L1. The same framework naturally extends to multi-class problems and practical evaluation using ROC and AUC. Despite its simplicity, logistic regression captures ideas that power much of modern machine learning.